Thermodynamics is a model developed to help understand the universe. Within thermodynamics, you have the first law, which says energy is conserved. In the universe, energy can be used to perform work, work can produce energy, but the total energy does not change. Energy can't be created or destroyed. The second law is more powerful. It actually gives direction to the first law. Through the second law, we find out that in the universe, any process that is thermodynamically possible must occur, and any process which is thermodynamically impossible can never occur. These concepts and the development of the two laws were covered in prior videos, which are linked in the description below. In the current video, we're going to look at how to implement the laws through various simple problems. For example, if I have 1 mole of an ideal monatomic gas initially at 25 degrees C and 1 atmosphere, and that gas expands reversibly to twice its initial volume, what would the values be for the thermodynamic variables of heat, work, internal energy, entropy, Helmholtz energy, and Gibbs energy, if this process occurred isothermally? Before we get into the nuts and bolts, there are 2 things to notice. First of all, thermodynamic principles only work on reversible systems. So for any question or problem, it has to be specifically stated that the process is recurring reversibly. Secondly, in order to be reversible in the real world, one variable has to be held constant. In this case, the process is being done isothermally. So, with those 2 things settled, here are the starting points, the things that are always true. First of all, the definition of work is always minus the integral of pressure times the change in volume. This led to the first law, which says the internal energy of a system is equal to the sum of the heat and the work, or equal to the integral of the heat capacity at a constant volume times the change in temperature. Also from the first law, enthalpy is defined as the change in heat at a constant pressure, or the integral of Cp dt. The second law gave us entropy. Entropy is defined thermodynamically as the integral of the change in heat over the temperature. From that, you get the Helmholtz energy, which is minus the integral of the entropy times the change in temperature, minus the integral of the pressure times the change in volume, and the Gibbs free energy, which is minus S dt plus volume times the change in pressure. In the current example, the condition given is isothermal. That means the change in temperature is 0. To use the laws, you look for which functions depend on temperature. For example, delta U and delta H all depend upon a change in temperature. Therefore, if dt is 0, delta U and delta H will be 0 for an isothermal process. Also from the basic definitions, the internal energy is the heat plus the work. So if the sum of the internal energy is 0, that can only occur if heat is opposite and equal to work. Since work is minus PdV, that means for this system, the heat must be plus the integral of PdV. Another fine point here, as mentioned, a reversible process has to have one and only one variable held constant. In this case, isothermally, temperature is being held constant. That means pressure cannot be held constant. If the temperature is not changing and the volume is changing, the pressure also has to change. This gets around, you can get around this by realizing you are talking about an ideal gas, where for 1 mole, PV is equal to RT. So you can make a substitution. Since dQ is plus PdV, pressure is RT over V, so you get the heat being the log RT times the log of V2 over V1. R, the gas constant, 8.314 joules per mole degree Kelvin, times the temperature has to be in Kelvin, 298, And in this particular case, since the volume doubled, V2 over V1 is simply 2. So you get a value of heat produced as 1,717 joules. And with that, for free, work is going to be negative of heat, since delta U is 0, so the work will be minus 1,717 joules. The third basic definition says entropy is the integral of the change in heat over temperature. Since I have a change of heat and I have a temperature, 1,717 joules divided by 298 Kelvin gives you an entropy change for this system of 5.76 joules per degree Kelvin. The fundamental definition of the Helmholtz energy also has a term of temperature in it. So under these conditions, the Helmholtz energy is simply going to be equal to minus the integral of P dV, or equal to the work minus 1,717 joules. Similarly, the Gibbs free energy has a temperature term in it. So the Gibbs free energy is going to be equal to plus VdP. In this case, once again, the fact that we're dealing with an ideal gas comes in handy. The integral of VdP, since V cannot be constant, winds up being RT over P dP, or RT times the log of P2 over P1. Since I have an ideal gas, P2 over P1 is going to be equal to V1 over V2. Put it another way, the log of P2 over P1 is minus the log of V2 over V1, or delta G is also going to be equal to work minus 1,717 joules under these conditions. So, using the basic relationships, you find the answers, and you also find out that given the condition, all of the answers are actually interrelated to each other. Once you found the heat, you also found the work, and the Helmholtz energy, and the Gibbs energy if you have an isothermal system. Reversibility, once again, requires keeping one variable constant, where the thermodynamic variables are pressure, volume, temperature, and heat. In the previous example, we held heat constant. Now we're going to take the same question. I have 1 mole of an ideal gas, 25 degrees C, 1 atmosphere, with its volume doubling, determining the value of the thermodynamic variables if this process were now to occur adiabatically. You still have the same basics that always remain true, the definitions of heat, internal energy, enthalpy, entropy, Helmholtz energy, and Gibbs energy. You go back to the condition. Adiabatically literally means there is no heat flow. So your first variable, dq, is going to be 0. Since your internal energy is equal to heat plus work, if work is 0, the internal energy is simply equal to the work. Or the integral of CV dt is equal to the minus and negative integral of P dV. Once again, since heat is constant, pressure can't be constant. So you take a ideal gas law substitution where pressure is RT over V, and you notice that the value of the heat capacity at a constant volume for an ideal gas is 3/2 R. Your R's are going to cancel. You cross multiply by T. You get the integral of 3/2 1 over T dt is equal to minus the integral of 1 over V dV. Or 3/2 log of T2 over T1 is negative log V2 over V1. Since the volume doubled, that's essentially negative log of 2. I know T1, so I can find T2. In this case, when the volume doubled, the temperature dropped to 188 degrees, or a change in temperature of minus 110 degrees Kelvin. I go back to my universal laws, again look for the laws that depend on temperature. Delta U is the integral of CV dt. Now that I have dt, I find out that delta U is minus 1,372 joules. Since everything's connected in the problem, since heat was 0, that's also going to be the value for the work performed by the system. Similarly, the enthalpy is defined as the integral of Cp dt, with the heat capacity at a constant pressure being 5/2 R and a change in temperature of minus 110 degrees. You get a change in enthalpy of minus 2,286 joules. The definition of entropy is the integral of dq over T. In this case, for an adiabatic system, dq is 0, so the change in entropy is 0. Since the change in entropy is 0, the Helmholtz energy simply becomes, once again, the work. S dt is going to be 0, so you get delta A is equal to minus PdV, or minus 1,372 joules. Same with the Gibbs energy. Since entropy is 0, the Gibbs energy winds up being the integral of VdP, which, since V cannot be constant if heat is constant, substituting from the ideal gas law, delta G is RT over PdP, or RT log P2 over P1. Some more gas law gymnastics. P2 over P1 is the same as V1 over V2. So the log of P2 over P1 is minus the log of V2 over V1, or once again, delta G is work, minus 1,372 joules. So again, those are all of the answers to the question, where the thing to bear in mind is that they were all related to each other, sort of like unraveling a thread. Once you find the end of it and you start pulling, all the other values come right out. So we've held temperature constant and heat constant, remembering that they're related but not the same thing. If I take the same system, my 1 mole of gas at 25 degrees C, and double its volume, this time at a constant pressure, where your fundamental relationships are always still going to be true for the definitions of heat, internal energy, enthalpy, entropy, Helmholtz energy, and the Gibbs free energy. In this case, you don't have very much that depends on pressure. But you are dealing with an ideal gas. Volume is related to temperature, where T2 over T1 is equal to V2 over V1. Or once again, since the volume doubled, in this case, to make the math easy, T2 over T1 is equal to 2. T2 winds up being 596 degrees, and you have a delta T of 298 degrees, which will help you, once again, once you know what dt is. Delta H is the heat at a constant pressure. Cp dt, 6,194 joules. Delta U, heat capacity at a constant volume dt, 3,716 joules. A little bit more gymnastics. The actual definition of enthalpy is the internal energy plus PdV. So if I know U and I know H at a constant pressure, the internal energy minus the enthalpy is equal to the work, in this case minus 2,478 joules. Entropy is dq over T. Again, one always has to be careful to note what conditions are being held constant. Since I have a constant pressure, the heat flow is the heat flow at a constant pressure. That's defined as Cp dt. So the integral of Cp dt is Cp log T2 over T1. And the change in entropy is 14.41 joules per degree Kelvin. Delta A simply now becomes arithmetic. Minus SDT minus PdV is minus SDT plus dW. I have a value for S, so it's minus 14.4 joules per degree Kelvin times 298 K, which was the change in temperature. and I have a value of work of minus 2,478 joules. So the Helmholtz energy for this process is minus 6,772 joules. Similarly, delta G, you have the fundamental relationship of minus SDT but plus VDP. However, since I have a constant pressure, that simply winds up being the entropy, 14.41 joules per degree Kelvin, times the change in temperature. So you get a change in the Gibbs free energy of minus 4,294 joules. Again, the point of these exercises is to simply show how all of the variables are related to each other through the thermodynamics equations. Okay. Questions that are actually more relevant to the real world are answered the exact same way. So far, we've held pressure, temperature, and heat constant. For volume, we're going to have to come up with another question. If we want to hold volume constant, let's say I have 1 mole of the ideal gas at 25 degrees C1 atmosphere, and it's compressed until the pressure rises to 2.5 atmospheres, this time at a constant volume, where all of my fundamental equations still hold true. They're always your starting point. And a constant volume means dV is 0. You look for things that depend upon dV, so the work is 0. For an ideal gas, pressure is also proportional to temperature. T2 over T1 is equal to P2 over P1. So if the pressure goes up by 2.5 times, the temperature also rises by 2.5 times. Its final temperature is 745 K. You now have a change in temperature of 447 Kelvin. Having a change in temperature allows you to find delta U and delta H, because fundamentally they are always defined as delta U being CV dt, delta H being CP dt. So given the change in temperature, the internal energy would increase by 5,575 joules. The enthalpy would increase by 9,291 joules. The entropy, this time dq over v is I have dq at a constant volume, would be the integral of CV dt, or CV log T2 over T1, giving a change in entropy of 11.43 joules per degree Kelvin. Delta A, I have an entropy and I have a change in temperature. The value of work is 0, so I get minus 5,108 joules. Gibbs free energy, you start with the fundamental definition. This time, volume is constant, pressure is changing. Again, ideal gas relationships. It was given that I had 1 mole of an ideal gas at 25 degrees C, and the volume stayed constant, which means it had a volume of 24.5 liters, where 1 liter is 1,000 cubic centimeters. So 24.5 liters is 0.0245 cubic meters. Pressure, a change in pressure of 1.5 atmospheres is a change in pressure of 151,988 pascals. So delta G is minus S dt plus P dV. I multiply cubic meters by pascals. I get joules. Delta G for this process is minus 1,390 joules. So those are all of the thermodynamic variables for this process done at a constant volume. So far, we've covered reversible processes that occur at a constant pressure, temperature, volume, and heat, which are the only 4 variables that you can vary or hold constant to create a reversible process. One last example. So previously we have seen how to use thermodynamic properties and thermodynamic functions since they only work on reversible processes. This is not especially practical or useful in the real world because reversibility means something's moving infinitely slowly and moving in both directions. So essentially nothing would ever get done. The real world does not have very many reversible processes. For example, the water rolls downhill, it does not go back uphill. So, if you have a real world problem, an irreversible problem, you have to create a reversible pathway. So, for example, I take 1 mole of an ideal monatomic gas at 25 degrees C, 1 atmosphere, and that gas moves to a state of 90 degrees C in 3 atmospheres. Determine the values of heat, work, delta U, delta H, delta S, delta A, and delta G for the process. Note very carefully that this question does not have the word reversible in it. Unless you are told specifically that a process is reversible, don't assume that it is. If it is not stated to be reversible, that process is irreversible. Things still stay the same, though. You still have your fundamental thermodynamic definitions: heat, work, internal energy, enthalpy, entropy, Helmholtz energy, and Gibbs energy. So what you have to do if you have an irreversible process is create what's called a reversible pathway. Essentially, break the process up into steps. In this case, I'm giving 2 variables that are changing. I'm giving temperature and pressure. Since I have 2 variables, I can break it down into 2 steps. The first step, I'll take the gas at 25 degrees C, 1 atmosphere, and reversibly bring it to 25 degrees C, 3 atmospheres, with a dT of 0. For step 1, I have a reversible isothermal process. With that definition, I already know for an isothermal process, the internal energy and the enthalpy for the first step will be 0 joules. Since I also know the internal energy is heat plus work, work is minus PdV minus RT log V2 over V1. For an ideal gas, you have an inverse relationship with pressure and volume. So work for the first step is minus RT log P1 over P2, or minus 2,722 joules. Since delta U is 0, and delta U is heat plus work, they have to cancel out. So if work is minus 2,722 joules, the heat transferred would be a positive 2,722 joules to get a delta U of 0 for this step. Once I have heat, entropy is defined as heat, change in heat over temperature. I have a change of heat, and the gas is being held at 298 K. So I have a change in entropy for the first step of 9.13 joules per degree Kelvin. Since the temperature is being held constant, delta A is simply minus PdV, or work. Similarly, from the work shown in the isothermal reversible process, at a constant temperature, minus PdV is the same as plus VdP. So for the first step, the Helmholtz energy and the Gibbs energy are going to be equal to the work, both equal to minus 2,720 joules. So my pathway, step 1, I change the pressure. Step 2, I change the temperature. I start with a gas at 25 degrees C, 1 atmosphere. First, I hold the temperature constant and change the pressure. Now I have a gas at 25 degrees C, 3 atmospheres. I hold the pressure constant and change the temperature. So I have a reversible process at a constant pressure. And I have a value of dT. 90 degrees at the end, 25 degrees at the beginning. I have a change in temperature of 65 degrees C. So delta U and delta H for the second step are simple to calculate. CV dt, CP dt. 3/2 R times 65 gives me 811 joules for delta U. 5/2 R CP times 65 degrees is 1,351 joules for delta H. I have also found pressure because the definition of delta H, CP dt, is the definition of the heat transfer at a constant pressure. So 1,351 joules. Delta U is heat plus work. I have a delta U and I have a heat. So work is going to be delta U minus dQp, or delta U minus delta H minus 540 joules. Entropy is the heat flow divided by the temperature. In this case, pressure is constant, temperature is not. Heat at a constant pressure is Cp dt. Cp dt over T is the heat capacity at a constant volume, log T2 over T1. I have T2, I have T1. I have an entropy of 4.1 joules per degree Kelvin. I have an entropy. I have a change in temperature. VDP is 0. I get a delta G of minus 267 joules. I have an entropy. I have a change in temperature. I also know the value of work. So delta A is minus 807 joules. So I've now created a reversible pathway, 2 variables in 2 steps. You first hold variable A constant. You then hold variable B constant. The final step for the entire process, you simply add up step 1 and step 2. So the heat transferred, 2,722 joules for the first step, 1,351 joules for the second step, is 4,073 joules. Work, minus 2,700 joules, minus 540, minus 3,262 joules. Delta U, 0 plus 811 is 811. Also, in this case, if you wish to check, the definition of delta U is dQ plus dW. If you add 4073 minus 3262, you wind up at the same 811 joules. Enthalpy, 0 plus 1,351 is a positive 1,351 joules. Entropy, 9.1 plus 4.1, 13.23 joules per degree Kelvin. Helmholtz energy, again, step 1, minus 2,722 joules. Step 2, minus 807 joules, is minus 3,529 joules. Gibbs energy, minus 2,722 minus 267, is minus 2,989 joules. I really hope this video was helpful. As mentioned, the thermodynamic theory is a way of understanding the universe and using that understanding to move forward, to make things, to build things, to create things. If it's thermodynamically possible, it can happen. So the purpose of this video was to show how you use those laws of thermodynamics in a real-world setting to actually get the answers. I hope you enjoyed this and found it quite useful.